like to report what we've been using Blue Waters for, and overall I would like to thank for the support and also for putting together this very nice meeting. We benefited from talking to the staff and got new ideas from in-person meetings. It was very useful, and overall the level of support, the computer time we got is spectacular. We totally benefited from Blue Waters' machine. It was one order of magnitude larger than we could get elsewhere, and we'll show you how we put the machine to use. The only comment I have is basically by the name of the machine. We walked around Dillon's Falls yesterday, and maybe the machine should have been labeled White Water rather than Blue Waters. So given that, I want to talk a little bit more about the details. I want to introduce Canonical Monte Carlo to you, and then talk about two applications we've done. We study materials at extreme conditions. And I will talk about CH plastic and also about hot dense silicon. The work's been done by François Sauviron, Kevin Driver, and Shuai Zheng, who actually moved on to Livermore. So the career pipeline worked, and computational skills actually are helpful to find new jobs. We get support from NSF DOE Partnership for Plasma Science and Engineering, and a generous support from the Blue Waters Grant. So to motivate this work, I'm showing the phase diagram of hydrogen. So what we try to understand is how do materials behave at extreme conditions. But quantum mechanics is important, and particularly I show here the temperature axis. So for example, Jupiter has 100 Kelvin on its visible surface and about 16,000 in the deep interior where the magnetic field is being generated. And then much, much hotter is the sun. You have 6,000 Kelvin on the visible surface and 10 million in the deep interior where the fusion occurs. What happens? Is that the connector? So, okay, just a bad connection, I think. So let's hope it will work. So Jupiter is of great current interest, and that's because there's the Juno mission in orbit around the planet, and it has about 30 flybys. It was launched in 2011, arrived last year, and it has since been orbiting the planet. And by every orbit it comes by, and there's different measurements. And one of the crucial ones for us is Jupiter's gravity field. And we construct interiors models to match the observed gravity field. And we want to understand questions like how big is the rocky core, and how many ices and planetesimals were needed to form the planet initially. It's also ironic that now the Cassini mission is doing a similar maneuver. They dive inside the inner ring, and they didn't crash into anything. Apparently, there's empty space, as one would hope, and they're doing the same gravity measurements, and we will construct comparative models now, comparing the two models as a result. So to construct models, we rely on ab initio simulations to say what hydrogen and helium do under these conditions. And the high temperature phase diagram is typically studied with Canonical Monte Carlo, which I'll tell you about today. It's based on Richard Feynman's work, who wanted to do superfluid helium at 2 Kelvin. And we are now applying this to millions of degrees Kelvin. So at lower pressure conditions, we have old-fashioned density functional theory that derives the orbitals and then moves the nuclei according to the equations, Newton's equations of motion. So I thought I'd give you a little bit of an introduction what Canonicals is about. Just to know that you know what goes actually into these Blue Water simulations. And I'm comparing the Boltzmann factor, that would basically that we see here, where it weights all the states available in your system. And if you want to derive an average, you have the classical partition function. On the quantum mechanical world, you have an operator, which is the density matrix, which is e to the minus beta h, where h is your Hamiltonian, rather the energy, and beta is 1 over kBt. And to evaluate it, you can use real space, for example, or you use the trace over the partition function. So it's all about this operator, which is Canonical, what it's based on. And it's very simple. What we do is we split that operator into a product of two operators, each having de facto beta over 2. And beta is then will become imaginary time. It's 1 over a kBt. And if you write this in real space, you remember from your quantum mechanics class, you have to insert one complete set of states. So it buys you have one density matrix and another one, you have integrate over all intermediate steps. So if you have this trick once, we can do this multiple times, and we can split this density matrix operator into 4 operators and have integration over 3 intermediate steps. Each time, the density matrix that governs this step is a temperature 4 times higher. And once you've done this 3 times, well, you can do it m times. So we split up the density matrix and insert m intermediate sets of states. And you have to integrate over all intermediate positions. And what it buys you is basically that we know the operator for a small step much higher, much more accurate. At high temperature, many body correlation effects are negligible, so we recover them by integrating over all possible intermediate states. And then we compute thermodynamic averages from the trace, which closes all those paths. So what you can think about it is the following. We have paths in our simulations that live in real space, x, y, and z, and then we have an imaginary time that basically links all these intermediate steps together, and it's the kinetic energy that lets these beads, ties them together, and at the same time, they're all interacting as usual. So the quantum nature arises because these paths are flexible and they're moving around. And the method is based on Feynman's fundamental work and also David Zeppeli's practical implementation. He's here to talk to. But I feel we should also give decent credit to Douglas Adams because he invented the infinite improbability drive, where the spacecraft flies to all possible points in space at once. And that's exactly what path angles are about. You have to explore all possible space. If you read Douglas Adams carefully, however, he doesn't tell you how to do fermions. Read the book, but for us, there's no information. So you have to basically go back what David Zeppeli did and add one more complication. And that's basically you introduce nodes, and you single out one starting point of your path, and then that sets a boundary for all other points on the path. And every time we move the path in Monte Carlo, we have to make sure we do not cross this node. It's been shown if the nodes are exact, you're solving the exact fermionic problem. And if they're approximate, you get a good approximation to your fermionic solutions. So we often use free particle nodes, and we also have more accurate nodes where we have bound orbitals. So the work is based on the team from David Zeppeli that made this method work for hydrogen, and our DE grant basically funds us to make it work for heavier elements. So 2 applications, we started out with water, and all what we want to do, we want to calculate what's the energy and what's the pressure for given density and temperature. And that's not simple at extreme conditions. So we run DFT codes like VASP that was mentioned this morning, to conditions of 1,000,000 Kelvin, where the author of VASP probably did not consider them as interesting. And then we basically run path integral calculations from top down. They're very efficient at high temperature, and then at lower temperatures, the paths get longer and the nodes are more challenging to handle, but then we get agreement. So we now have, for the first time for water and carbon, we have a method where we can spend the whole temperature range with ab initio simulations. And we can do more accurate predictions for shock experiments than is possible with pen and paper theory. So we get good agreement for pressure, we get good agreement for the energy, but we also look at these pair correlation functions. So for a water plasma, we can look at hydrogen, water, and oxygen, hydrogen, and this measures how repulsive are the nuclei. And if you overlay our path integral results, then we get an extremely good agreement. And this is remarkable because one code has classical nuclei and orbitals, and the other code has path. The nuclei are very localized, but the electrons are path. They don't talk to anything. They're totally different approximations in both codes, but at the end, if you apply them in the same conditions where they both work, you get very consistent results, which is sort of always the benchmark for all results that we publish. So we've done it since for a number of materials, carbon, nitrogen, oxygen, lithium fluoride, and neon, and then we compare with shockwave experiments. So shockwaves are a way to study materials at this high pressure and high temperature at the same time. And our colleagues in Livermore have various ways to generate these things. Here is the old-fashioned gas gun, where a projectile hits something, and that launches a shock in the material. And then moving on, they switched to lasers, and they could generate 3 million atmospheres. And at Zandia, they have the biggest battery on the planet. And when they short-circuit this battery, there's such a gigantic current, it drives a magnetic field that expels an aluminum plate, and the aluminum plate hits something. That's how they generate their shocks. And if this isn't enough, then you can go to the National Ignition Facility, which is the biggest laser on the planet, has the size of a football field, and it hasn't quite made ignition yet. It triggered nuclear reactions, but no consistent burn wave yet. But it is a wonderful machine for high-pressure experiments. So what happens in these shock experiments, you have a projectile that actually pushes into the material, and you have a jump from an initial state to a final state, and then conservation of mass, energy, and momentum allows you to derive the density, pressure, and energy by only measuring how fast your shock wave is traveling and measuring how fast your projectile is traveling. This is remarkable. 2 velocities, and you get an absolute equation of state measurement. And that's important because at the end of your experiment, nothing is left. These projectiles travel at multi-kilometers per second. There's nothing left from your sample when you're done. And then we plot the results in pressure density space and compare the experimental points with the theoretical points that we derive. We solve the last equation here and put points on this diagram. So how did it work for CH plastic? CH plastics are important because they coat the capsule where the liquid fuel in a fusion experiment is stored. So all the laser beams, they're hitting the inside of a hole round, X-rays being generated, and they drive the shock in the material. And there's this CH layer that sort of encloses the liquid fuel in a fusion experiment. You want to know how CH behaves. So, and this is part of what we've done. And here's where your blue water times went. We basically did many points in pressure and density space. And here you have the pathological results, and you have the density functional results. And this is for one material, and this is what we typically do with an allocation and a typical machine. But with blue waters, we could actually change the composition of the plastic and repeat all those calculations for a number of relevant conditions. So blue waters, the amount of time and the accessibility allowed us to actually have 1 order of magnitude more of computer time, which we invested in studying many CH ratios, which we couldn't do anywhere else. So here are the results that we got. First of all, these are the old theories that were predicted. They're much simpler. They don't run often heavy-handed computation. Here we have existing experimental results. The largest experiments on the NOVA laser have a huge error bars. They don't constrain the theory very much. But these are the latest measurements at the National Ignition Facilities. They reach about 700 megabars and have this shape. So 2 sets, one led by Thilo Döppner and the other one by Annie Creature, and the lower and the high temperature results. And this is what we found. So we agree with the lower measurements, and we see a rollover in this Hugoniot curve that's triggered by the L-shell electrons, so the 2s, 2p being excited at these conditions. And you have this huge excursion here. That's when the 1s electrons from your carbon atoms get excited. So as you may notice, we don't have perfect agreement. I don't know why that is. But the moment it's useful to have theory in the experiment, it's probably the theory is so much cheaper because any point on here costs multiple $100,000. So the theory is cheap in comparison. So we will still figure this out. We are not sure why we have a discrepancy. We agree with one set of experiments, but not with the highest results. So for silicon is the other material. I want to talk about it a little bit. Silicon has 14 electrons, so we have to treat the core electrons better. And we improved the fermion nodes by using hard-to-Fock orbitals, and that improved our overall agreement with the density functional theory. And once again, we compare the internal energy and we compare the pressure so that we have methods, the methods both agree with each other, and then we calculate these shock Hugoniot curves. So here are results from existing equation of state tables. And basically, what we find is that when we add our results, we get a very high compressibility. And we find the L-shell electrons get excited, that pushes the curve here. The material becomes very compressible. Then there's a little bit of a dip where it goes back, and then the K-shell electrons get excited. And if you compare with an orbital-free method, which is another popular technique at the moment, they get the overall excitations, but they're missing the shell effects because that's not included in this otherwise very efficient method. We compare results with Livermore. We have Jerry Starrett's work that we compare, and it's very favorable under many conditions. So overall, what we can say, we do this equation of state calculations, and we compare these shock Hugoniot curves, and we have results for helium, where we see as the electron gets excited, we get a big excursion. For carbon, we see one bump that comes from the 1s state. Then for nitrogen, we see the molecules that excited. That happens around lower temperatures. Then the L-shell electrons and the K-shell electrons get excited. And then this repeats itself for oxygen and for neon and also for silicon. So overall, we invest this time to derive the properties of materials at extreme conditions. And we also, the benchmark is always to get reasonable agreement between these two methods. And that means that the pressure is off by no more than 2%, and then the energy agrees to better to 5 Hartrays per atom, which is a humongous amount by low temperature calculations, but it's not very much if you talk about highly excited electrons. And then we find no serious problem with the zero temperature exchange correlation functionals that's always used in Kohn-Sham DFT. And we're marching along to get the methods to work for heavier elements. So important for us was blue orders because it provided a 1 order of magnitude increase in computer time. And we invested this in more complex materials. For example, heavy elements like silicon, and that allows it to put more physics in these nodal surface calculations. And then in this other case for a CH, which has not so many electrons, we invested it actually to do many CH ratios at once, so that when the experiment is to a different type of plastic that has a different C to H ratio, we already have the results. So we could solve and settle this problem once and for all. So thank you very much.